All right, in this video, we're going to be working the extra practice for BC Homework 10.3, and it's going to be a lot of meaning of the polar derivatives. Drd theta, dy dx, dx d theta, dy d theta, all sorts of derivatives. And it all is going to go back to this diagram here. And it says that the figure here shows the graph of r equals f of theta, where theta is between 0 and 1.8. And the graph of r equals 1. So I'm going to just label those right now. R equals 1, we know that's a circle with radius 1 centered at the origin. So I'm just going to put that there, r equals 1. Okay. And then the other one is r equals f of theta, and I should have a different colored pen ready. And that's going to be the black curve. Okay, so this is r equals f of theta. Okay, and it's going to be asking you about various derivatives and values at different at each of these points. Okay, and it's got 24 of them. I'm going to do number 25 as well. It's more algebraic, and maybe I'll add a couple of them in if I see any that catch my eye. But I'm pretty sure 24 will be enough derivatives. Okay, so let's get this up. The first one is going to be value of theta at point A. Okay, at point A, so it says that f runs as theta runs from 0 to 1.8. So it's either the case that h is 0 and a is 1.8 radians, which doesn't really seem very reasonable, right? We know that theta 0 radians is here if r is positive, and back here if r is negative. So I'm going to say that at A, theta equals 0. And the instructions say, determine whether these things are positive, negative, 0, or don't exist. Okay, I'm going to say, right, f of theta at point A, that's r, the value of r at point A. And so since we know that theta equals 0 at the beginning of the curve, and I'm over here where x is negative, I know that r is negative as well. And since r is f of theta, that's going to be negative. Okay. Number 3 is f of theta at point B. F of theta is r. And we're right here at the origin, so that means that r is 0. Drd theta at point B. Okay, so that's what's the rate of change of the distance from the origin as theta increases. Okay, so as theta increases, we go from A to B to C. And also, r is going from negative to 0 to positive. So that means that r is increasing as we pass through B, meaning r's derivative with respect to theta will be positive. And I feel like, there's a bunch of these, so I'm going to probably just start writing plus and minus. Number 5 is dy d theta at point B. Okay, dy d theta is, you're thinking to yourself, as theta increases, what's happening to y? Okay, well, it looks to me like y, we're going up a little bit. It's not very big, but y is increasing as we move through point B, because down here you can see y is negative, and over here y is positive. So I'm going to say it's also positive. Okay, number 6 is f prime of theta at B. At B? No, okay, yeah, at point C. Okay, f prime of theta, that's the exact same as drd theta, right? Because r equals f of theta. Okay, so this is the same idea. Is the distance from the origin increasing or decreasing? And I think it's pretty clear that the distance from the origin is increasing as we move through point C. And as we the idea of increasing theta on this curve f of theta is A to B to C to D to H. So f prime at C is going to be positive because the distance from the origin is increasing. 7 is dx d theta at point D. Yeah. Okay. All right. here at point D, you can see that we're here at a place of vertical tangency. That's one thing you might notice. And we know that at a vertical tangent, dy dx doesn't exist because of division by 0. But we also know that dy dx equals y prime divided by x prime, where x prime is dx d theta. So now I'm saying that dx d theta is probably 0 because of the vertical tangent. But I could also say that over here, we're kind of at a maximum in x. We're at the maximum x coordinate. And if we're at a maximum and it's smooth, then the derivative is probably 0. So that's another reason that dx d theta at point D is going to be 0. All right, let's move these up a little bit. 8 is dy d theta at point D. Okay. dy d theta is positive because as I move from C to D to E, at point D, y is increasing. Okay, so I'm going to say that's positive. 9 is dy dx at point D. Okay, this is not going to exist because it's a vertical tangent. Also, you could say it's not going to exist because dy dx is dy d theta divided by dx d theta, which is a positive number divided by 0, which we know doesn't exist. Number 10, drd theta at point E. Okay, drd theta. Are we getting closer or farther from the origin at point E? And, well, that one's, let me think about how I want to say this. All right, so you notice that E is kind of sitting tangent to the graph of the circle. It's really the first time that gray circle has come into play. And I think that what I want to do is zoom in on the point E. Let's see how far this thing can zoom in. Can it keep going? I mean, it's getting closer and closer. Okay, that wasn't the best. I was hoping I could really zoom in, and you see that like near point E, the two curves are essentially the same. Okay, and so, you know, since they're both having this particular behavior right here at E, it would stand to reason that drd theta, or that the derivatives would be the same. That drd theta for f would be the same as drd theta for r equals 1. And r equals 1, we know how to take the derivative of a constant. That's 0. I think that, yeah, that's the level I'm usually zoomed in at. And so since drd theta for the gray circle is 0 at point E, it stands to reason that drd theta for f at point E is also 0. Okay. You could say that, you know, yeah, moving in a circular way is how drd theta is 0, and at that instant it's moving in a circular way. I don't know, I might be saying the same thing over and over again, but either way, this one's going to be 0. All right, number 11 is dy dx at point E. dy dx is the slope of the tangent line. Okay, and, you know, if I just laid in a tangent here, it would have a negative slope, so I'm going to say that dy dx is negative. Okay, number 12 is dy d theta at point E. Okay, at point E, looks like as we're moving through here, well, I mean, you could even think about the tangent line. As I move that way, y is going up. Okay, so because I'm moving right to left and I've got a negative slope, whatever. Y is increasing as I move through here. So I'm going to say that dy d theta is positive. All right, number 13, dx d theta at point E. Okay, dx d theta is negative for the same reason, right? I'm moving this way and I'm going towards the y-axis. From places where x is positive, that means x is decreasing, so its derivative is negative. Also, I'll point out that because dy dx is negative and dy d theta is positive, it stands to reason that dx d theta would have to be negative because dy dx is dy d theta divided by dx d theta. Let's see, 14 is dy dx at f. Dy dx at point F, that's 14, okay. At f, okay, I'm seeing a horizontal tangent. So dy d theta is going to be 0, and dx d theta I think is still going to be negative because I'm over here where x is still decreasing. Or I could say, okay, it's just the slope of the tangent line, and that's 0. I think that's probably the better way to think of it. But I bet it's going to ask us for, yeah, some other stuff at point f. Okay, dy dx is equal to 0. But and it said dx d theta for number, yeah, for number 15. Okay, dx d theta is negative because I'm still moving right to left. Okay, it's not on here, but I'm just going to throw this out there. dy d theta at point f is 0, and that's how we got dy dx equals 0, because we're at kind of a maximum in y. Number 16 is going to be dy dx at point G. Okay, dy dx at point G, okay, it's pretty steep and positive, so I mean, yeah, and it's got a positive slope here, the tangent line, so I'm going to say that dy dx is greater than 0. 17, dy d theta at point G. Okay, at point G, y is going to be decreasing, right? We're moving to f to g to h. Okay, our y coordinate is decreasing, so dy d theta is going to be a negative number. You know what? I'm just going to also point out, before I move on to number 18, find my eraser. Yeah, here we go. I'm just also going to point out that dx d theta is also going to be negative at point G. Okay, and then a negative divided by negative gives us a positive dy dx. Okay, it's negative. It's probably not very negative because, you know, it's not decreasing by that much, x, but x is still decreasing. I am moving right to left. Okay, this is drd theta at G. We'll talk about drd theta in a second. Am I getting closer to or farther from the origin at point G? And it sure looks to me like I'm getting closer to the origin as I'm moving through f and G. So if the distance from the origin is decreasing because I'm getting closer, then drd theta would be negative. All right. Yeah, and that would be the same as f prime of theta at point G. Number 19 is theta at point H. Okay, to answer the question directly, it's going to be positive, but I could be even more specific and say, I would say theta equals 1.8 because that's the end of the graph, and it told you that you're looking at the graph of f of theta from theta equals 0 to theta equals 1.8. Number 20 is f of theta at point H. Okay. I'm feeling like this is positive. Okay, because as I'm over here at h, this is 1.8 radians evidently, and that seems reasonable because I know 1 radian is up here somewhere near pi over 3. This is, you know, where r is positive. This is pi radians. Okay, so it's, you know, I'm over here where I'm expecting to be. If I saw point h down here, where theta was equal to 1.8, I would know that r was negative. Okay, and therefore f would be negative. But now I know I'm, okay, theta equals 1.8 is approximately here. I'm going forward along that line. That's going to be a positive r value, positive f of theta. 21 is going to be drd theta at k. Okay, that one's going to be 0 because, well, think about r equals 1. drd theta is the derivative of 1 with respect to theta is going to be 0. So drd theta is always 0 on that circle. And because it's a constant distance from the origin. Okay, the distance from the origin not changing. Okay, dy dx at point k. Okay, dy dx at point k, I put in a tangent line. It's got a negative slope, so dy dx is negative. 2023 is dy d theta at k. Okay, as we move, through the unit circle, right, we know it has this orientation to it, this counterclockwise orientation. So as I move through point K, y is decreasing. So I'm going to say dy d theta is negative. Hopefully 24 is dx d theta, yeah, at point K. Okay, and at point K, x is increasing because I'm moving left to right. So I'm going to say that that's positive. And then dy d theta divided by dx d theta is going to be a negative number, which is what I saw when I did dy dx. Okay, so that was, a good set of problems. It's a really good set of problems last year when they were having to do online quizzes. Lots of good discussion on that problem set. So, all right, number 25 is suppose r equals f of theta is a polar curve with a vertical tangent at theta equals pi over 6. Okay, this is very related to a problem from the 10-3 homework that is related to a multiple choice question that I've seen the past couple of years and that I've really liked. But I'm taking it a step farther here. So it's going to be if f of pi over 6 is equal to 4 root 3, find f prime of pi over 6. Like, how am I supposed to do that with only the information that there's a vertical tangent? And it's not just that f prime of pi over 6 doesn't exist, right? That would not be a question that would be worth asking you, especially on the extra practice. So I'm going to, let me see, I'm going to zoom out and maybe move my face. So I'm going to say, if there's a vertical tangent, that's dx d theta equaling 0. Okay, dy dx non-existing because of division by 0, and we know dy dx is dy d theta divided by dx d theta. Okay, so I'm just going to need dx d theta to equal 0, but I need to start with x. X is r cosine theta, but r is f of theta. So I'm going to say x equals f of theta times cosine theta. Okay, then I'm going to take the derivative of x with respect to theta, okay, which is dx d theta. Okay, maybe I'll write that in the next line. Okay, but I'm going to use the product rule. I'm going to take the derivative of f first and leave cosine the same. Then I'm going to add in, leaving f the same. The derivative of cosine theta is negative sine theta. And now I've got all the pieces I need, right? Because when I plug in pi over 6, I know what cosine and sine are because I know how to, evaluate trig on the unit circle. And they gave me f of pi over 6 here, so I'll be able to solve for that knowing that it's equal to 0. Okay? Now, it's one of those like Algebra 1 or physics problems where they give you everything but one and you solve for the last. Okay, so I'm going to say then, okay, dx d theta at the point where theta equals pi over 6 is going to be f prime of pi over 6, which is the thing I'm hoping to solve for eventually, times cosine of pi over 6. So I'm going to go over here and I'm going to draw you a little unit circle diagram. Okay, right here. We know pi over 6 is pretty low down on the unit circle. And it makes a 30, 60, 90 triangle because it's a pi over 6 or a pi over 3. And we know that for 30, 60, 90 triangles on the unit circle, the hypotenuse is 1, the short leg is a half, and the long leg is root 3 over 2. Okay. Maybe I'll even label that. Okay. Now that I've got that, I know cosine is adjacent over hypotenuse times root 3 over 2. Okay. Minus f of theta, we said was 4 root 3, times the sine of theta is a half divided by 1. Okay. And I know that that needs to equal 0, right, in order to have a vertical tangent. So I'm going to say, let's clean this up. This is 2 root 3 here, so f prime of pi over 6 times root 3 over 2 equals positive 2 root 3. Okay, so my first step is going to be divide both sides of this equation by the square root of 3.
and then multiply by 2. And I'm going to say f prime of pi over 6 is going to equal 4.
Okay, that's how we did that one.
Okay. That's all I got for you. Thanks for watching.